Wanted to make sure y'all knew we were recording. Are you really?
Okay.
After that, we're like, thank you. Appreciate it. So you should have a copy of the slides that were shared with you in your group chat. With me. By WhatsApp, group chat, I don't know. I'm recording in Zoom, so hopefully I'll be able to load Zoom recording into Blackboard later. If not, we'll just email it to all of you somehow. I'll get it to you somehow. All right, I have 1 o'clock and I am going to start because we have a lot of slides, practice problems to get through. So let's begin. And so this is chapter 13 in your book. And this is IV infusions, parenteral admixtures, and rate of flow calculations. These calculations are the same calculations you've been doing all along. We're just adding some new terminology into the mix just to shake things up a little bit. So once we start working on these, how many of you have already worked on some of the homework problems? Awesome. One person. Thank you, Claudere. So you'll see that these are just the same skills that you've been working on all along. It's just now we're applying to IV infusions. Good morning or afternoon. So we're going to be performing calculations on adult and pediatric infusions, critical care IV solutions, additives to IV solutions, and rate of flow calculations for IV infusions. Okay. So we're going to be working a lot with time when we were working on rate of flow. So thinking about injections, we are usually talking about aqueous and non-aqueous solutions that have additives added into them. And and they can come in many, many different forms. As you can see, there are vials, there's auto injectors, there are ampules, there are syringes that are pre-filled. And we can inject in almost every part of the body. Those terminology and those definitions, if you want to review them, are in your chapter. I didn't put all of those in here. And they really aren't necessary to do the calculations, but eventually you're going to need to know intrathecal, intraosseous, and all of those areas for injection. here is a table from your book on some of the more common solutions, and then I added on the left a table that I think is helpful when you're thinking about these different solutions and whether they're hypertonic, hypotonic, what their osmolality is and how they're used or what they're used for, just to give you a little bit more information about these types of solutions. I'm sure a lot of you are familiar with these already, because you probably have worked with them in a job of some sort, at the hospital, or in some sterile compounding capacity. And if you haven't, that's okay too, because you will pick it up very quickly. And as we're going through and we're talking about the different solutions, usually I think I only have like the most common ones in some of the example problems. We'll talk about what the abbreviations stand for, so you can get used to it. So we're gonna start off with just a little practice review, I guess. How many, and on this problem, we're looking at how many grams of dextrose and sodium chloride are used to prepare each of these 1 liter baths. And I went ahead and set it up for you just to remind you that we're using ratio and proportion for most of these, or a lot of these. And if you see D10 or D10W, that's dextrose 10% in water. And then normal saline is our sodium chloride, and it's 0.9%. Okay. So work those out and tell me what you get for the one on the left. The dextrose, how many grams of dextrose? Okay, that would be 100 grams. And then how about for the sodium chloride? 9, correct. So if you set up your ratio and proportion, like I have it here, and you cross multiply, those are the numbers that you should get. So what does that mean? That means that on the left in our bag that has dextrose 10%, that in the entire liter of fluid, we have 100 grams of dextrose. Next week, when we talk about nutrition, we're going to take it a step further and talk about how many calories that has. Okay, so we'll be expanding on some of this next week. And so on the right, you can see that we have 9 grams of sodium chloride in a liter bag of normal saline. Okay, so here's another one. We're going to practice. I didn't give you the setup for it on this one. So how many grams each of dextrose and sodium chloride are used to prepare a half liter or 500 milliliter bag of D5 1/2 normal saline? So in the same bag, okay, we have 500 milliliters, we have 5% dextrose and a half normal saline in the same bag. This is very common fluid that's ordered in the hospital setting for IV infusion, for fluid replacement. Okay, so for dextrose 5%, what did you get for your answer? How many grams of dextrose are in a 500 milliliter bag? Okay, so that's 25 grams. And then what about for the half normal saline, which is equal to 0.45%? Okay, so that is correct. So for this one, you could simply just take the 5%, which is 5 over 100, times your 500 mLs, and that gives you 25 grams. You could also have set it up ratio and proportion, just like we did on the previous slide, okay? And then for this one, it's the same thing, except don't forget that you have to divide by the 100 for your percentage conversion, and then, times 500, and that equals 2.25. Okay, simple enough. I will, these will be saved and I will upload them into Blackboard later, so you will have all of these annotations. All right, so let's work on this one. Hopefully you can see that on the slide. I can barely see it myself, but we're looking at a half liter of sterile water for injection on the right. That's what it would look like without any additives added yet. And we're trying to create a 12.5% dextrose solution using the 500 milliliters, which is a half a liter. And we have the dextrose vial, and we're going to add enough of that vial to the 500 milliliters to equal 12.5%. Okay, and the vial contains 500 milligrams per ml, because it's very hard to see, so glad I put it on there. Okay, so the first thing that I did was determine amount of drug needed or dextrose needed. Okay, so in this final product, we want the final percentage to be 12.5%, right? So I took the 500 milliliters, which is the half liter, and then I multiplied that by the 12.5%. Oh, sorry, let me fix that. I'm a little crazy on my decimals here. All right. Right, and what did y'all get? For how much dextrose is needed? How many grams? 62.5 grams, that's what I got, so good. And then you can just set it up in a proportion if you want, a ratio and proportion, so 0.5 grams, which is 500 milligrams per milliliter. And then we have the 62.5 grams in X milliliters, and that will tell us how much of this we're gonna pull out and add to this. And how many milliliters is that? It's 125 milliliters. So I'm gonna need 125 milliliters of this product. So I might have more than one vial necessary for that, but that's how much we would add to this. Do I need to remove any of this to keep the concentration at 12.5%? That's not part of the question, but if I wanted to maintain this to be 12.5%, I probably would have to remove 125 milliliters out of the bag to keep the volume at 500 milliliters. Does that make sense? Because if not, then we would have 62.5 grams of dextrose and 625 milliliters, and that would change our concentration. Okay, so we're going to be minusing 125 milliliters from the bag. All right, you ready? Move on. Any questions about this one? Okay. All right, so the next examples that we're going to, or problems that we're going to work on are going to be pertaining to micro and macro drip sets. So as you can see on the picture on the left, we have some tubing that go with infusion sets. And you have this little roller clip here that helps control the rate. And so this part right here will plug into the bottom of the IV bag and has a preset amount of drips or drops per milliliter. So when we're talking about micro drips, you can see the drip size is very, very small, and we would need 60 drops to equal a milliliter. And on the left, it's depending on the calibration of the drop set or drip set, anywhere from 10 to 20 drops per milliliter. So you can see the drop size is bigger, okay? So here we have a calculation. I'm going to let you try to do it on your own first, and then I'll help you out. Calculate the total drops in the delivery of 250 milliliters of an infusion when using an administration set calibrated to deliver 15 drops per milliliter. And if you want to go ahead and work on the second one, calculate the number of drops delivered each minute if the infusion lasts 2 hours. Okay, so for the first one, we know that we have 15 drops for every milliliter. And we're gonna deliver 250 milliliters. So you could say 15 drops per milliliter times 250 milliliters. And what did you get? You get 3,750 drops. Okay. The other way you could have done it is set it up with ratio and proportion. So 15 drops, 1 milliliter is equal to X drops and 250 milliliters. And it would give you the same answer. Okay. Then how did you determine how many drops will be delivered each minute if the infusion is to last 2 hours? So how many minutes is 2 hours? Okay. And then what did you do with that number? Divide it into what'd you get? Okay, and that's drops per minute. Because this is minutes, this is drops. Did everybody get that? Good. All right. All right, so sometimes we just do something called an IV push, where we will just inject the drug directly into the infusion set, and we don't have to mix it with anything, we can just push it. Sometimes it's a slow push, and it would be in the orders. So some medications have to be pushed, could be pushed very fast, like over 30 seconds or a minute, and then some have to take a little bit longer. But usually we're just pulling it right out of a vial, and then we're just pushing it, okay? So the very first question here says a physician orders enalapril 0.75 milligrams IV push for a hypertensive patient. So enalapril is the IV form for enalapril that is antihypertensive that comes in an oral formulation that should be on your top 100. Okay. How many milliliters of injection should be administered? And on the second one, we're looking at an order for midazolam hydrochloride, 2 milligrams IV stat. How many milliliters am I going to take out of this vial to get my 2 milligrams? So I'll let you work on those. Okay. These are still another same calculation, ratio and proportion. If you wanted to do it that way, there's probably other ways that you could do it. But we know that our enalapril in this vial comes in a concentration of 1.25 milligrams per milliliter, and I need 0.75 milligrams out of that vial. So 1.25 milligrams in 1 ml is equal to 0.75 milligrams in X mLs. So that equals what? Okay, 0.6 milliliters. So if I pull out 0.6 milliliters out of this vial, it will give me 0.75 milligrams to push. Okay. For this one, we know that we have 50 milligrams per 10 mLs of midazolam, which is 5 milligrams per milliliter. And I need 2 milligrams out of that vial. And how much is that? Point what? 4. Awesome. You did it. Okay, so if I pull 0.4 mLs out of this vial, it will contain 2 milligrams. Okay, all right. All right, so here are some images that are straight out of your book on what IV setups look like. I'm sure you've seen one of these before, either personally with a family member in the hospital or yourself, or you work in a hospital and you've seen these. You're not going to be tested on any of the components or any of the terms on these pages, but it's just nice to be able to see what it looks like. As you progress through the curriculum, you'll have opportunity to actually play with some of these bags. You have a serial compounding lab in your 3rd year that you'll be able to do some of this and work with some of these. So it is good to know, though, that you have like a primary IV bag, and then you can have a secondary IV bag that kind of like piggybacks onto that one. And so you might see like a fluid being hung, maybe normal saline will be in this large bag. Sometimes it'll have additives added on top of that, sometimes it won't. And then you may have like an antibiotic over here on a secondary bag because that only runs for a short period of time. And so they will connect it and run it with the fluid. So that way the patient only has one entry point, okay? It's less invasive for the patient that way, then we can do that. The problem is you have to make sure that whatever this fluid is that's running is compatible with the piggyback, okay? So those are some of the things that you'll be learning in the curriculum and you will be expected to know on your NAPLEX. And I believe if you've taken the CPHT exam, then you know that this is also something that could pop up on that exam as well as far as compatibilities. And then we also have pumps. These are going to be pumps that we can use for things like pain medications and sometimes like chemo medications, high-risk medications. And we program the pump to deliver a certain rate, either milliliters per hour, or it could be per minute. It could also be drops. And so we have the capability of programming that and making it more precise for the patient, especially in those high-risk medications. All right, so let's talk about rate of flow and practice 1 here for calculating drops per minute, okay? So we're looking for drops per minute for a medication order for 1,000 milliliters of D5W, so that's 5% dextrose, administered over 8 hours. We're using an IV administration set that delivers 10 drops per milliliter. How many drops per minute should be delivered to the patient? All right, I'm gonna move on because we getting halfway through the class period already here. And I want to get to some of the more complicated problems at the end. So we know that we have 1,000 milliliters that needs to be administered over an 8-hour period. I just set it up as like a dimensional analysis problem. You could have just gone ahead and pre-calculated how many minutes are in 8 hours if you wanted to, and put that here instead, but that I just went ahead and took the extra step here to do the conversion. Okay, and we know we have 10 drops per milliliter. Okay, and so if setting up my dimensional analysis, if my end is drops per minute, I know I set it up correctly if I have drops on top and minutes on bottom. Okay, so crossing out all of these, what do you get? Okay, 20.83 drops per minute. Now on a quiz or an exam, you might be asked to round up to the next, up or down to a full drop. Or you might be asked to round to the nearest tenth or 100th. Okay, but for that, we got that. Any questions about that? All right. Y'all are doing great. And I knew you would. Okay, so here is a picture at the top. You can see that we have a sterile hood and we have a technician or a pharmacist adding an admixture to an additive to the bag. And we're actually wanting to add amphotericin B emulsion. And you can see that it's 50 milligrams per 10 mLs, which reduces to 5 milligrams per ml. And so we have an order for our patient weighing 154 pounds, and the order calls for 0.25 milligrams of our amphotericin per kilogram of body weight. So we have 0.25 milligrams per kilogram of the patient's body weight. And we're going to put that in 500 milliliters of our D5 injection. And so we want to know how many milliliters of the available amphotericin B needs to be added to the dextrose. So I need to know how much of this gets added to that. first thing that I did was convert my weight to kilograms. So 154 pounds divided by 2.2 pounds per kilogram. 70 kilograms. So that's how much the patient weighs. Our dose is what I calculated next for the patient. So patient's dose. And that's 0.25 milligrams per kilogram times 70 kilograms. And that equals 17.5 milligrams. Is everybody with me so far? Awesome. All right. So now I need 17.5 milligrams out of this vial over here. Okay. So I know it has 5 milligrams per 1 ml. And I need 17.5 milligrams. And I need to know how many milliliters to pull out. How many did you get? What's your answer? 3.5. That's what I got. So if I pull 3.5 milliliters of this, it will give me 17.5 milligrams of amphotericin that I can add to that bag. Got it? All right, moving on. Another example. So nicardipine is administered in the acute treatment of hypertension by slow IV infusion at a concentration of 0.1 milligrams per ml. We have a 10 ml vial that is containing 25 milligrams of nicardipine and needs to be added to what volume of D5W? So we need to figure out what size bag of D5W we need to achieve our desired concentration of our infusion, which is 0.1 milligrams per ml. It's a little trickier. Kind of like a backwards question. Okay. So we know that our desired concentration is 0.1 milligrams per ml. Okay. And we want to know what our final volume needs to be if we add 25 milligrams to a bag to keep this concentration the same. Okay. So it should be 250 mLs is the total volume. But we probably are going to subtract out the 10 ml vial from that to keep our concentration the same, and we would end up only needing 240 mLs of D5W because we're adding a 10 ml vial of nicardipine, which holds the 25 milligrams. Wow, that does not look like nicardipine. Okay, so if you had a question like this, I would probably give you a hint to make sure that you are accounting for all of your volumes for your final answer. Okay? Does that make sense? Okay, we want to try to keep the concentration, the final concentration, we want to keep it the same if possible, you know, because that's, especially when we're looking at really small concentrations, 0.1 milligrams per ml. All right, let's move on to the next one. Here's another weight-based dosing. We have a patient that weighs 87 kilograms and needs dopamine at a dose of 4 micrograms per kilogram per minute from a bag containing 100 milligrams of the medication and 500 milliliters of D5W. How many milliliters per hour should be infused to provide the desired dose of dopamine? So we're looking for milliliters per hour. That's our final answer. Not that far, y'all with me so far on this one? So you calculate the dose needed for the patient in micrograms per minute, which was 348. And then you want to convert that to milligrams per hour. And then we're gonna calculate how many milliliters per hour, okay? Does anybody have a final answer? Yeah, you got it, 104.4, and that's milliliters per hour, right? Milliliters per hour. Good. That one was a little bit more steps. All right. We're going back to our basics back here. We're gonna refresh on some concepts. So how many grams each of sodium chloride and dextrose are present in a 500 milliliter IV bag of 0.33% weight per volume sodium chloride and 3% weight per volume dextrose? Tell me what weight per volume is again? Per. So these you could set up ratio and proportion. You could just say 0.33% is equal to 0.0033, and then take that times your volume. And what does that give you? For the sodium fluoride? 1.65 grams. And then we could just do the same thing here, 5%, 0.05 times 500. And what does that give you?
It's 2%.
Oh, yeah, 2%, sorry.
3%.
Shh, 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 shh. I'm being recorded. I knew that, okay. 15? Oh, yeah, okay. Like right there, in front of my face, okay. You got that? Okay. All right, we got a two-stepper here. All right, so this is a patient weighing 176 pounds to receive dobutamine 3 micrograms per kilogram per minute. The available solution contains 100 milligrams of the medication and 250 mLs of D5W, and the calibration of the IV tubing is 50 drops per milliliter. Question 1, how many milligrams of dobutamine will the patient receive per hour? Okay, milligrams per hour. That's what we were looking for. And then how many drops per minute? Will the patient receive? And I'll help you. The patient weighs 80 kilograms. Okay. So on the first question, we need to calculate our dose from the patient's weight, which is 240 micrograms per minute. And then I converted that to milligrams per minute because my final answer needs to be in milligrams. So I divided by 1,000 and got 0.240 milligrams per minute. Okay. The question asks how many milligrams per hour. So then I converted 60 minutes in an hour and got 14.4 milligrams per hour. Is that what you got? Okay. Then the next question says, how many drops per minute will the patient receive? So we have 0.24 milligrams per minute, but we need to convert that to drops. And so we know we have 250 milliliters with 100 milligrams and 50 drops per milliliter. So I just set it up in dimensional analysis and I got 30 drops per minute. Anybody else get 30 drops? Good job. We're gonna move on. So we got limited time. All right. The next one is a patient is to receive 750 milliliters of a half normal saline over 12 hours. How many grams of sodium chloride would be administered per hour? Okay, so half normal saline is the same as 0.45% sodium chloride, which is 0.45 grams in 100 mLs. You can use ratio proportion with the 750 mLs and you get 3.375 grams, but that's over 12 total hours. We want to know how many per hour. 0.28 grams per hour. Y'all get that? Thumbs up. All right. I am going to skip this one and I want you to work on this next one. This one has milli equivalents in the equation, so I want you to do that one. While you're doing that, I'm gonna write the answer out for the one before, so you'll have it when I upload the slides. Will that work? You have it on your, okay. Perfect. Give you a hint. What's your valence? Yes. Definitely do not have perfectionism when it comes to my handwriting on your slides. Do better, I'm sorry. Okay. What I need is to know how many milliequivalents this 10 grams is. That's gonna be added to this 150 milliliters of normal saline. Okay, so if I just plug in, I have 147 over 2, divide by 2 or over 2, and then my milligrams is 10,000 milligrams. Okay, I just multiplied this by 1,000. And then that will give me my milliequivalent that I need. What did you get? Nick, you look like you have the answer.
I got 45.
45.4.
What did y'all get? You got 45? For the milliequivalents here? Or for your total volume? I'm not finished. This is just the first part. Oh, you didn't do that. Okay. All right, so did anybody do this part?
106.05.
Okay, 136. I'll fix that. All right, so then what did you do? 3 milliequivalents? Or did you do it? How did you do it a different way?
5 to 136.3.
This should be the 45. Is that what you got? 45.35? Close? Can't read that. Okay, because the final answer is milliliters. How many milliliters of calcium chloride? Okay, so if we administer or add 45.35 milliliters of calcium chloride, that will give us the right amount of milliequivalent. Or vice versa. Yeah. All right. One more bonus question. Last one. So you should have gotten a half a unit in 20 minutes. Because we have 12 units being administered over a total of 8 hours, and we just need to convert our 8 hours to minutes, and then we can multiply that to 5 20 minutes. Clearly, the recording